In section 5.1, we talked about the natural log. We defined the natural log. We figured out a bunch of properties of the natural log, and we talked about derivatives. In section 5.2, we're going to talk about integrals. All right, so does anybody remember from Calc 1, this is a function that did not show up very often, the absolute value of x. Anybody happen to remember the derivative of the absolute value of x? No, I didn't think so. It doesn't show up very often. The absolute value of x, as you recall, looks like a big V, like so. Where it has the point 1, 1, 2, 2, so on and so forth. Negative 1, 1, negative 2, 2. If x is a positive number, if x is over here, what's the derivative? 1, because it's just the slope of that line, isn't it? And what if x is a negative number? It would be negative 1. All right, so we could write the derivative this way. 1 if x is positive, negative 1 if x is negative. And what if x is 0? Undefined. Why is the derivative undefined at 0? Well, there's a couple good answers. One answer would be there's a sharp corner right there. And that was our way of recognizing when functions did not have a derivative. The other good answer would be if I'm taking the limit as x goes to 0 of the derivative on the right, I'm getting 1 and 1 and 1 and 1 and 1. If I'm taking the limit as x goes to 0 from the left, I'm getting negative 1, negative 1, negative 1, negative 1. Or negative 1 and positive 1 the same thing? No. All right, but the way this is normally written, the derivative is normally written as a function that way. F prime of x equals absolute value of x over x. Why are those the same thing? Well, pick your favorite positive number. What's your favorite positive number?
4.
4. If you plug 4 in, what's the absolute value of 4?
4.
What's 4 divided by 4? 1. Pick another favorite positive number. 13. What's the absolute value of 13? 13 divided by 13 is 1. So it certainly works for positive numbers. Now give me your favorite negative number. Negative 273. What's the absolute value of negative 273? What's 273 divided by negative 273? Negative 1, so it works there too. All right, so quite often the derivative of the absolute value is written in that form. All right, so that's going to lead me to this. G of x is natural log of x. And we said if g of x is the natural log of x, then the derivative is
1 over x times x prime.
1 over x times x prime, but in this case, x prime is the number 1. All right, so I like your answer, though. So if g of x is ln of some other function, not just the letter x, then g prime of x is 1 over f of x times f prime of x. Excellent. So now, combining all that stuff together, what if g of x is the ln of the absolute value of x? 1 over
Absolute value of x over x. So it's 1 over x.
So it turns out to still be 1 over x, doesn't it?
Crazy.
Crazy. All right. We define because of what we just showed. The integral of 1 over x dx, which is the same as the integral of x to the negative 1 dx, to be the natural log of the absolute value of x. And of course, we always throw a plus c on the end. So that fixes the power rule that we had in Calc 1. In Calc 1, we had a power rule for integrals, and the power rule worked as long as the power was not the number negative 1. So here's our rule, power rule, when the exponent is the number negative 1. Why do you think it's important that we put that absolute value in there? We just showed that the derivative of the log of the absolute value of x was 1 over x. But it's also true that the derivative of ln of x is 1 over x. So why do we define this integral to have that absolute value in there? Why don't we just leave it as ln x? Any ideas why we want that absolute value in there?
So it follows the rules up top.
Not really.
Because ln of x isn't what you said yet. Like it's always an increasing function. Or something.
It is always an increasing function. That's true.
And it doesn't exist on the negative past.
You cannot plug negative values into this original ln x, can you? Can you plug negative numbers into here? Yes. And the reason we want that is maybe, for some reason, we want to take the integral from negative 2 to negative 1 of 1 over x dx. If I defined this antiderivative to just be ln x, would I be able to plug in those two negative numbers? No. That's why we really want those absolute value symbols there. It allows us to use this rule for any numbers, except for 1. There's still one bad number. 0. ln of 0 is still undefined. So that's why we had those little absolute values on there. It allows us to talk about definite integrals where our x values are positive. It also allows us to talk about definite integrals where our x values are negative.
Why can't you use negative numbers?
What's the definition of logarithm? What's the domain? X has to be positive numbers. That's the way we define logarithm. In that integral from 1 to x, and x had to be a positive number because we didn't want to cross 0 because there was a vertical asymptote at 0. Okay. Anyway, so this would be ln of 1 minus ln of 2, which would be minus ln of 2. Because the ln of 1 is a nice number, ln of 1 is 0. Okay? So that's why we want to slip that little absolute value thing in there. That little absolute value allows us to have definite integrals where we have negative values. Questions on that? All right, well, this leads to some nice things. Back in Calc 1, we liked this function sometimes, f of x equals tangent x. And we said the derivative of tangent is secant squared. However, back in Calc 1, when I wrote that symbol, we were stumped. What's the antiderivative of tangent x? Well, back in Calc 1, we didn't have an answer. In Calc 2, we're going to have an answer. I'm going to write tangent x as sine x over cosine x. And then I'm going to do a little u substitution. What should u be? If you're going to do u substitution, u is almost always the bottom. So I'm going to let u equal cosine x. And then du would be negative sine x dx. So I need to sneak a negative in there to make that one work, which means I need to put a negative out here. So I end up with negative the integral of 1 over u du. What's the integral of 1 over u du?
U to the negative 1.
It is the same as u to the negative 1. Okay, so this is negative integral u to the negative 1 du. What's the integral of u to the negative 1? What was the integral of x to the negative 1? ln absolute value of x. So the integral of u to the negative 1 is ln absolute value of u. So this is minus ln absolute value of u plus c, which means the final answer is negative ln absolute value cosine x plus c. So we now have a nice formula for the integral of tangent. Questions on that? All right, so I'm going to make a new list here. We just showed that the integral of tangent x was minus ln absolute value of cosine x plus c, which is sometimes written as the ln absolute value of secant x plus c. How are those two things equal? I got rid of the minus, but where would that minus go? It would go in and it would become a negative power. So I would have cosine to the negative 1, which is the same as 1 over cosine, and 1 over cosine is secant. Usually you see it written in the negative ln cosine form, but every now and then you'll see it written in the secant form. You could do the exact same trick. I'm not going to work it all out. You could write cotangent as cosine over sine. Do the exact same trick. Your u substitution would be u is? No. Just u. What would u be? U would just be sine. U would be the bottom. But then the derivative of sine is cosine. So you're not going to end up with a little minus this time, are you? That little minus came from the derivative of cosine on bottom. So this one's just going to turn out to be ln absolute value of sine plus c. Questions on that? All right, integral secant x dx. Let's see if we can figure that one out. And then we'll have an integral for cosecant x dx, and that'll be all of them. Unfortunately for cosecant, or for secant, I mean, it's not quite that easy. Because I could write secant as 1 over cosine, but then I'd have a problem, wouldn't I? Because u would be cosine, but then when I take the derivative, I'd end up with a negative sign. I don't have a negative sign anywhere to make that substitution, do I? All right, so for secant, we do something crazy. See how you like this. We're going to write this as secant x. Then I'm going to multiply it by the number 1. And I'm going to write the number 1 in a very strange way. I'm going to write the number 1 as secant x plus tangent x divided by secant x plus tangent x. Is that the number 1? It is equivalent to the number 1, and does multiplying by 1 change anything? No. Then I'm going to let u be that new bottom that I just made up. U is secant x plus tangent x. And then look what happens. du is, what's the derivative of secant? Secant tangent, so that's secant x tangent x plus, what's the derivative of tangent? Secant squared x dx. Look what I happen to have on top of this thing that I wrote here. What's secant times secant? Secant squared. What's secant times tangent? Secant times tangent. So this entire numerator here, this secant times secant plus tangent dx, all of that becomes du. And then what do I have on bottom? Just u, don't I? So this becomes the integral of 1 over u du, or I could write it as du over u. What's the integral of du over u? Natural log absolute value of u. So this is natural log absolute value of u plus c. So the answer turns out to be the natural log of the absolute value of secant x plus tangent x plus c. Told you that one wasn't so easy. Anybody want to venture a guess on cosecant?
Pretty similar thing.
Pretty similar. What changes?
It's minus 10?
You're going to have a minus.
Or is it 10 minus? Because
No.
So cosecant should be cosecant minus 10.
It's going to be cosecant and cotangent. But you're going to have a minus sign out front because the derivative of cosecant is a negative cosecant cotangent. And the derivative of cotangent is negative cosecant squared. So it's minus ln absolute value cosecant x plus cotangent x plus c. And you would derive it exactly the same way if you want to take the time to write it down and convince yourself that I'm not lying to you. Questions on that? All right, so that fixes all the trig functions. We now have antiderivatives for all 6 trig functions. Of course, we already knew the antiderivatives for sine and cosine. All right, so some of the problems in your book are going to have trig functions, but a lot of them won't. A lot of them are going to look like this, perhaps. You're going to have the integral of x over x squared minus 3 dx. Any ideas on what to do? U. U is? U is almost going to be always going to be the bottom on these problems. So U is going to be x squared minus 3, which means du is 2x dx. So I need to sneak a 2 in here to give me my 2x dx, which means I need a 1/2 out there to balance it out. That's going to be 1/2 integral 1 over u du. What's the integral of 1 over u? Natural log absolute value of u. That's right. So we're going to have a 1/2 natural log absolute value of x squared minus 3 plus c. Questions on that? All right, let's try another fun one. How about, here's one that this is similar to the one you were asking me about, Charles. How about the integral of you want me to do that exact one? Sure, read it off to me.
2x squared plus 7x minus 3 over x minus 4.
quite often you're going to let u be the bottom. I'm going to need more space. If u is x minus 4, then du is dx. So that gives me a u down here on bottom. Gives me a du right here for this dx. What am I going to do with all this stuff on top? I can't bring it out front because it's got variables in it. If it was just a number, I could bring it out front. It's got x's in it.
Solve for x over here.
It's that common trick that we did before. We're going to take this and write x is u plus 4. So on top, every time we see an x, we're going to write u plus 4. So we're going to have the integral of 2 times u plus 4 squared minus or plus 7 times u plus 4 minus 3, all divided by u du. I told you I was going to need more room. So we have the integral of 2 times u plus 4 squared plus 7 times u plus 4 minus 3 all over u du. And one might look at that and say, holy crap, that looks worse than what we started with. How do we make it better? I'm going to FOIL here and distribute the 2 through. I'm going to distribute that 7 through. I'm going to combine all my terms up on top, and then I'll see what I can do. All right, so integral. By the way, this is the hard way to do this one. And in a minute, we'll do it again, and I'll show you what I think is a slightly easier way. But what you were doing works.
Okay.
Not wrong. I think it's the harder way. So this is 2 times u squared plus 8u plus 16 plus 7u plus 28 minus 3 all over u du. And the second way is not a lot easier, so don't get excited. This is the integral of, I'm going to have 2u squared, and then I have 2 times 8, that's 16, 16 plus 7, 23, plus 23u. 2 times 16 is 32. 32 and 28 is 60. 60 minus 3 is 57. All over u du. All right, so I did all that FOIL, all that distribute, combine all my like terms that you told me to do. Looks better, but not great. Now what? Divide each term by u. That's right. And that's why you want to do a u substitution. You want to have just a u here, because then you can divide each term individually. That's the advantage of having a u as opposed to a x. What did we start with? An x minus 4 on bottom? All right, so that's going to be the integral of 2u plus 23 plus 57 over u du. And now we can integrate. What's the integral of 2u?
U squared.
U squared. Plus, what's the integral of 23u? Plus, what's the integral of 57 over u?
57 natural log u absolute value of u plus
57 natural log absolute value of u plus c. And finally, we plug our x's back in. What was u again? Was it x minus 4? So we're going to have x minus 4 squared plus 23 times x minus 4 plus 57 ln absolute value of x minus 4 plus c. Questions on that?
in 5.2.
What's that?
That one's in 5.2 homework.
That is a 5.2 homework question. That's correct. All right, let's do that problem again. What was the original problem? Integral of 2x squared plus 7x minus 3 divided by x plus 4? X minus 4?
Yeah, X minus 4.
X minus 4 dx. Okay, here's a slightly easier way to do this problem, I think. Generally what we do when we notice that we have a polynomial divided by polynomial, and the polynomial on top has a bigger power, generally what we do is we divide. We do the polynomial division. Anybody remember how to do polynomial division? Well, you divide polynomials just like you divide numbers. So I'm going to write 2x squared plus 7x minus 3. And I'm going to divide by x minus 4. Okay, so you deal with the leading terms. I need to put something here, and the something I need to put here, when I multiply it by x, I need to get 2x squared. So, or 2x. So I take 2x times x, that's 2x squared, and then 2x times minus 4 times minus 4 is minus 8x. And then what do? Subtract. What's 2x squared minus 2x squared? 0. What's 7x minus negative 8x? 15x. And this is where people will make the mistake, they'll put minus 1x. But it's 7 minus negative 8. So that's 15x. And then you bring down the minus 3. And then I need something times x to give me a 15x plus 15. So that's 15x minus, what's 15 times 4? 60. And then I subtract 15x minus 15x, that's 0. Negative 3 minus negative 60 plus 57. That's a familiar number. I've heard that somewhere before. All right, so 57, that's your remainder. So what we have is we can rewrite 2x squared plus 7x minus 3, all divided by x minus 4, is the same as 2x plus 15 plus 57 over x plus 4.
Why is it x plus 4? 57.
X minus 4, I'm sorry. Thank you. X minus 4 there. And now we integrate. What's the integral of 2x? What's the integral of 2x? X squared. Plus, what's the integral of 15? 15x. Plus, what's the integral of 57 over x minus 4? It would be, because I'm going to put in a couple steps for this one. That's really a U substitution problem, because I don't have just the letter x down on bottom. If I had just the letter x down on bottom, I'd be okay. I could just use my ln. But since I have something else that's technically a U substitution, U is going to be x minus 4, but it works out perfectly because du is 1 dx. I don't need to slip any little extra number in and divide by that same little number. So this becomes x squared plus 15x plus the integral of 57 over u du. So when you do your u substitution, it works out perfectly. You do just get the ln that you mentioned. So final answer, we have x squared plus 15x plus 57 ln of x minus 4 plus c. Which way was easier?
Just depends on if you remember when you do the division.
If you don't know how to do division, then the first way is a lot easier. If you can't do it the second way, that's right. But if you can do the division, I think the second way is easier. And you're going to need to learn to do the division at some point anyway. When we get into chapter 8, I believe, and we talk about something called integration by partial fractions. It will have to be set up so that the power on top is not bigger than the power on bottom. You'll have to do that sort of division anyway. So you might want to get used to it. But I have a good question. What's the same answer?
Yeah,
Yeah, my guess is they are. If you FOIL here and distribute and combine all your like terms, you should get x squared plus 15x. So I do think they are the same answer, they just look different. Questions on that? Okay. The integral. Of ln x over x dx. What do you do? Question number 1, I guess, is do you need U substitution?
You can use your substitution, it was just an x. I think there was just an x on bottom.
You can't use U substitution when there's just an x on bottom?
So you can say that u was just x.
You can never say U is just the letter x. That's correct. That doesn't do you any, well, you can say it, but it doesn't do you any good at all.
But it's not just x, it's ln times 1 over x, and you substitute 1 over x, can't you?
I can let U be 1 over x,
Yeah.
since that x is on bottom. I can. I don't think it's going to help, though. That's x to the negative 1. When I take the derivative, I would get negative 1 x to the negative 2 dx. And I don't think that helps me with that ln at all.
You can let u be ln of x because then you end up with the derivative being 1 over x.
All right, so the moral of the story is U is not always the bottom. And this is a good example. What you want to do with this one, this is a U substitution. What tells me this is U substitution is I have division. Because we don't have any quotient rule, do we, for integrals? But you're right. U should be ln x because the derivative of ln x is 1 over x dx. You need to watch out for that. U is not always the bottom. When you have a fraction, is U going to be the bottom most of the time? Yes. The vast majority of the time when you have a fraction, U will have something to do with the bottom, but it's not always. All right, so this becomes the integral of U du. What's the integral of U du? 1/2 U squared plus C. So the answer is 1/2 ln of x squared plus C. Okay, so don't fall into the trap of thinking U always has to be the bottom. That's not the case. How about this one? The integral of there's so many good ones here. 1 over x ln x cubed dx. Any thoughts about that one?
Ln x cubed is u.
You want to try u equals ln x cubed? Let's see if that'll work. Du would be, what's the derivative of ln of x cubed? It would be 3x squared over x cubed, because it would be the x cubed goes to the bottom, and then you multiply by the derivative of x cubed, which is 3x squared.
So it would be 3 over x.
So it would be 3 over x dx. So I need to sneak a 3 in right here to have a 3 over x, which means I balance it with a 1/3. So once again, u was not the entire bottom. U in this case was just part of the bottom. And a mistake a lot of students will make on this one, they'll see the fraction, they'll let u be the whole bottom. And that's not going to work. So this becomes 1/3 the integral of 1 over u du. So that's 1/3 ln absolute value of u plus c. So this is a weird little answer here. This is 1/3 ln absolute value of ln x cubed plus c. So you have an ln within an ln. Don't see that very often, but it happens. Questions on that? What's the integral of ln x dx? I'm glad nobody said 1 over x. That's the answer I usually get. How come the integral of ln x is not 1 over x? That's the derivative of ln x. The derivative of ln x is 1 over x. What's the integral of ln x? Give you a hint, it's a trick question. We don't know. So, the moral of the story is, if you see an integral symbol and you see an ln in it, you're going to have to use u substitution, and u has to be the ln thing. So if you see an integral and that integral has an ln in it anywhere, you better be that ln thing, because you don't know how to find the antiderivative of ln.
Is that a we in Calc 2 don't know, or no one knows?
We don't know yet. There is an answer.
Does it involve e?
It does not involve e, although that's a very good guess. It does not involve e. Sometime when we get into Chapter 8, I believe, we will talk about something called integration by parts, which is the reverse of the product rule. Remember, a product rule from derivatives, we'll learn the reverse of the product rule, and using integration by parts, we will be able to find that antiderivative. I can tell you're all, so I'll just tell you the answer. I can tell you're all upset.
Doesn't look so bad.
Doesn't look so bad.
What about the process to get that?
Process to get that, actually integration by parts isn't too bad. That's one of the easier techniques. You're going to like integration by parts a lot more than you like integration by trig substitution. I promise you that.
I'm just wondering why we can't just not know. I would have just.
You can live the rest of your life without knowing that?
If we don't know what the integral of the natural log of x is, then we don't know.
And we don't.
Human curiosity.
Okay, so here, I'll make you feel better. There you go. Keep the mystery alive.
So is that like $1 million proof?
No, don't waste your time. Because it has been proven that this does not have an antiderivative. Not only does nobody not know what it is, people have shown that it doesn't matter how hard you work, you can't find one. There isn't one.
It's the unprovable.
It's There is not an algebraic function that you can write down that has that as an antiderivative.
Just making your own very complicated.
Well, there's, you said
Okay.
there's no algebraic function.
Correct.
So is there a trick? Is that loaded?
No. As far as I know, there is absolutely no answer to
See, you
that.
guys read into it. Just
Because-
accept it.
Because like E is its own derivative, isn't like because E is its own derivative and antiderivative, unless it's on antiderivatives.
Correct, and we will talk about E in the very near future, derivatives of E's and integrals of E's. But you have to believe me that that's one that doesn't exist.
I believe you. They might not. But
And it's kind of unfortunate because if you put a minus sign in front of that, it's still nobody knows. It still doesn't exist. But that's kind of an important function. And what's important about that function is it looks like that.
Oh, Elder.
Anybody know what that is?
Normal
It's what?
curve. Normal curve.
That's the normal bell curve. And if you take the integral would be the area under that curve. And if you take any statistics, area under the normal curve gives you the probability.
that's crazy.
So it's unfortunate that we don't know an antiderivative of that because it does give us probability. So we have to use our things like Simpson's rule and trapezoidal rule and things like that to approximate. Unfortunately, we cannot use that fundamental theorem of calculus that we like so much because there is no antiderivative for that function. Questions on that? All right, we got time for one more, I think. How about, let's see, I saw another good one here. I like this one a lot. The integral of 1 over x to the 2/3 times x to the 1/3 plus 1. Any thoughts on that one?
Make U the stuff in the parentheses,
Why do you want to make u be the stuff in the parentheses?
because then the antiderivative of the x to the 1/3 would be x to the negative 2/3.
You said antiderivative, but you meant derivative, and you gave the derivative,
Yeah.
which would be this thing. Yeah, in general, u is usually going to be the thing that's more complicated. Or in this case, what you're really looking at is when I take the derivative of this piece, I'm going to get that piece, and that's what you really want. But in general, u is the more complicated thing, and that's certainly because that plus 1 more complicated. So we take our derivative, du is 1/3 x to the negative 2/3 dx, which is 1/3 times 1 over x to the 2/3 dx. So we do get that x to the 2/3 down in the bottom. Now the penalty is I need a 1/3 in here, which tells me I gotta sneak a 3 out there. 3 integral 1 over u du. 3 natural log absolute value of u plus c. So final answer is 3 natural log absolute value x to the 1/3 plus 1 plus c. Questions on that? All right, my last warning on this section. Ron Larson decided he was going to be cute every now and then. Every now and then, there are problems in here where you do have to use U substitution, but you will not end up with an ln. So he throws a few of those in there just to keep you on your toes. Not every answer in this section is going to have an ln in it.
I got one.
You got one? Which one?
X over square root 30 minus x squared.
That's correct. That's one that would not have an ln in it. So watch out for that. Every now and then, there's a few problems sprinkled in there
You know,
to keep you awake. Questions on that?